Welcome to the third lecture of module 1 in the course Low Voltage CMOS Circuit Operation. So, the module 1 is on MOSFET, weak and moderate inversion regions, and this lecture 3 is basic charge model. In today's lecture, we would cover MOSFET surface potential in all the regions of operation and surface potential as a function of gate voltage. So, basically we would be using EKV formulation, which is found to be more suitable for explaining weak and moderate inversion. In the previous lecture, lecture 2, we had discussed that the electric field at the interface, silicon dioxide interface, is given by this value, and this electric field is essentially vertical or transverse in the device. And the reason is that we are considering a long channel device and gradual channel approximation, as we had discussed in the previous lecture. So, this, as we discussed in the previous lecture, this term, first term, is because of inversion charge, in this case electrons, and the second term is because of hole charge in this case, and the third term is because of depletion charge. And we define this part, this whatever is there under the square root, as a function f, which and this is a function of potential 2 phi f and v. So, what is phi f? Phi f we had discussed in the previous lecture, that it is the Fermi gap. It represents the difference between EI and phi f. Okay. So, if doping density increases, p type doping density, then phi f also increases. What is this V? V we had discussed as, now there is a VDS which is applied, positive VDS. So, V is the local surface potential. So, here it is 0 and here it is VDS, in between we are calling it as V, and V keeps on increasing from the source edge of the channel to the drain edge of the channel, as we had discussed in the previous lecture. Ut is the thermal voltage, LD is debye length, we have defined it in the previous lecture. So, as you increase V, so V increases from the source edge of the channel to the drain edge of the channel. As you increase V, what is the impact? Exponentially the electron density reduces. So, this charge is electron charge. Where is it? This electron charge is in this channel region, and because of the transverse electric field pointing downwards, the electron charge, you can say, would be confined to the interface, silicon dioxide interface. Now, this we will justify more as we go ahead in this course, and this is an area charge that we are measuring. So, we are looking from the top, and we are measuring the area charge. So, that is why we had integrated a function, integrated the Poisson equation, and that is how we have obtained this. So, this is an area charge, we look from the top, and the area charge is given by this expression. So, charge in silicon, how much is that? So, that is, since this is the electric field pointing downwards at the interface. So, if we have a Gauss cylinder here, okay, and so then, as we had discussed earlier, the bottom lid would have a 0 electric field, the sides, these two sides would have electric field which is vertical, and therefore, their surface integral of electric field comes out 0 for the bottom lid and these side surfaces. For the top lid, there is an electric field Ez, and therefore, Ez into the area of the lid is the surface integral of electric field on this entire Gauss cylinder. So, we can directly therefore relate Ez to charge per unit area. So, that comes out to be epsilon silicon into Ez, Poisson equation or Gauss law. Okay. So, this is Gauss law, and since the electric field is pointing downwards, this is a negative charge. So, what happens when the value of this surface, this potential increases? So, potential would increase as you move from the edge of depletion region towards the interface, the potential would keep on increasing, and potential would also increase at each location if the gate voltage is increased. That we will discuss in more detail later. So, the potential would increase from the edge of depletion region here and till the interface. Okay, so this chi. So at the interface, we will call this chi as chi s, surface potential. So as you increase the value of surface potential, you could have increased that by increasing the gate voltage. So when you increase that, what happens? So let us look at this first term. Exponentially, you can see that exponentially this first term keeps on increasing, this term keeps on reducing, second term, and this increases linearly, this third term. So you would find an increase in charge density or the contributed by the electron charge. So why are we saying so? We had actually, this is the integral of electron charge in the Poisson equation. We had written Poisson equation in the previous lecture, and we integrated from the edge of depletion region here till the interface. So in that Poisson equation, the electron charge term resulted in this. So this is the electron, this represents the electron density of, looking from the top, the electron density per unit area. This represents that. This represents the whole density per unit area, looking from the top, and this represents the depletion charge per unit area, looking from the top. So this as chi increases or chi s increases, surface potential, looking from the top, the electron density per unit area increases exponentially. When does this dominate? So this anyway, when you keep on increasing the surface potential here, this becomes negligible, because the value of chi s is quite large compared to thermal voltage, which is 26 millivolts. So if you increase chi s, the first term increases, and when does the first term become comparable to the depletion charge, that we can see. So as soon as chi s is larger than, say it is say 3 times ut, you would say that exponential chi s by surface potential by thermal voltage is much larger than 1. So you can just say that the first term is exponential chi s by ut into exponential. Now as you keep on increasing chi s, and when chi s is equal to what comes out, you find that this becomes close to 1, close to unity. This first term gets close to unity. So and beyond this, when you increase the value of chi s further, the first term starts increasing the value of the first term starts increasing exponentially. So since the value of the third term increases linearly and the value of the first term increases exponentially from a value 1. See, the first term has obtained a value, has gained a value 1 when chi s is equal to 2 phi f plus v. Okay. At this location, the local surface potential has increased to v. It was 0 here, it is BDS here, and here it is v. So when chi s is equal to 2 phi f, this first term becomes equal to 1. After that, when you increase chi s, it increases exponentially from 1, and this third term, which is depletion charge per unit area looking from the top, this third term increases linearly with chi s. So soon you would find that the first term becomes larger than the third term. So that we call as onset of strong inversion. Now suppose we increase v by a certain value, delta v, then you would increase this by delta v. So the value of chi s at which the first term starts to dominate and increase the value of this f exponentially. See, so when this 2 phi f, what is the value of 2 phi f? We will calculate that soon. You would find that 2 phi f typically would be much larger than, very large compared to thermal voltage. So therefore, 2 phi f plus v by ut would be a value which is very large compared to thermal voltage. So therefore, chi s becoming larger than this value. So chi s would also be quite large compared to thermal voltage when this happens. Okay. So and there the first term becomes 1, and now when you increase chi s further, first term would exponentially grow from 1. So we want to find what is the value, when does this, so when you increase the value of chi s here, this direction. So when you increase the value of chi s, you would first find that chi s is smaller than 2 phi f plus v at a location, say this location, and therefore, the function f would look more or less like when chi s is smaller than 2 phi f plus v. Now, you increase and f would approximately be equal to 1 when chi s is equal to 2 phi f plus v, and f would be proportional to exponential chi s by 2 u t exponential minus 2 phi f. So, if when chi s becomes larger than 2 phi f plus v, then we find that soon it outgrows the value of chi s by u t, and then it, because this is an exponential function, soon you will find that the other terms, this term is negligible and it is only this term which matters. So, therefore, f would be, function f would be proportional to this now, because this one also you can neglect. So, therefore, this is proportional to this. So, you would find that there is an exponential relationship. So, that is what you find, this is a log scale, you find an exponential relationship here. And what about the relation here, f versus chi s? So, there, this is the region where chi s is smaller than 2 phi f plus v, and therefore, this term dominates. So, it is just like a square root law. When does this transition take place? This transition takes place after chi s is greater than 2 phi f plus v. So, that a kind of threshold exists when chi s is equal to 2 phi f plus v. So, if we increase this v local potential by delta v, that is, we are moving from this point to say this point, we increase the local potential by delta v by moving towards the right. Then what happens? Then chi s is equal to 2 phi f plus v plus delta v would also shift, the value of chi s would also, at which this first term becomes 1 would also shift by delta v. That is why this strong inversion for v is equal to 0, that is at the source edge of the channel, is shown like this, and exactly after v plus u t, that is, you have applied a voltage. So, the local surface potential here is v. Now, exactly after u divided by v t, u t, that is normalized value of v normalized with thermal voltage, you find that this shifts by that much value. So, because you are increased chi s here, and when you increase this, so critical value of chi s at which this becomes, this first term becomes 1 also moves by v. So, that is what we are observing here. Now, let us try to understand this somewhat quantitatively. Let us take an example device. So, the example device in the book by Enns in this reference has a phi f of 14 u t. In our example device, we will have a phi f of 18 u t. Okay. So, with this example device, we will do some calculations to understand what we have discussed just now. So, channel length is this, so it is fairly large. So, you can apply long channel approximation. Body doping density here, we are assuming it to be uniform and this much, which also corresponds to the typical values seen in planar devices. Phi f is, this is the difference between E I and F p. So, this is equal to F p minus, so this is the value of phi f, and L d is the debye length. We had defined it as, this way, we had discussed this in the previous lecture. So, with these values, when you calculate, you will find it to be 2.9 nanometer. VFB, we have taken the flat band voltage. What is this flat band voltage? I will discuss that in the coming slide. So, we have taken it to be minus 0.7 volts, which is a typical value, and TOX, oxide thickness, this we have taken it to be 10 nanometers, and COX, the oxide capacitance per unit area, which is epsilon oxide divided by TOX. Okay. So, this comes out to be 0.345 microfarad per centimeter square. Now, let us find out the value of the electron charge per unit area, its contribution to F, and the contribution of hole charge to F and the contribution of depletion charge to F for different values of the surface potential chi s. So, now let us first look at the value of surface potential chi s is equal to 1.5 phi f. So, it is not 2 phi f, we are looking at 1.5 phi f. Here we find that the first term e to the power first term is equal to nearly 6 into 10 to the power minus 10 to the power 11, and let us calculate this 2 phi f by ut. This comes out to be nearly 2 into 10 to the power. Suppose the drain voltage VDS is 0.1 volts. Suppose for all the cases we take VDS 0.1 volts. So, in that case at the drain edge of the channel you get this value. So, the first term this nearly comes out to be 12. If the value of V is 0, that is at the source edge of the channel, we find that the first term this nearly comes out to be 12 into 10 to the power minus 5. So, as you can see, as we move from source edge of the channel towards drain, for the value of local surface set potential increasing by just 0.1 volts, there is a there is almost a two-fold increase in the, there is almost a 2 orders of magnitude increase in the value of the first term, which represents electron charge per unit area. So, you can see that by within the channel, just by increasing the local surface potential by a value V, you find that the increase in carrier electron charge or increase in the first term is quite large. Okay. But what is the value of the second term, the third term which represents depletion? What is its value? Its value is, in this case we have taken the surface potential to be 1.5 f. So, what is the phi f? So, that is 18 into 1.5, so 27, right. So, this is, so the third term has a value 25. Now, that is quite large compared to the values that we are seeing. See, the first term's value is this for V being 0.1 volt, that is at the drain edge of the channel, which with VDS is equal to 0.1 volt. So, from source edge of the channel to the drain edge of the channel, there is a order of magnitude reduction in the electron or in the value of the first term. But we also see that though there is an order of, though the electron charge density per unit area or the first term is increases by around 2 orders of magnitude from drain edge, when we move from drain edge of the channel to source of the edge of the channel, even here the first term is negligible compared to the third term. So, therefore, it is the third term which dominates F here in this region. Though you are increasing the surface potential, the third term dominates, and at this point the third term, first term assumes a value 1, and after that soon it takes over the third term, and therefore, you find that after that it is only the first term which is dominating and which is showing this. Okay. Now, let us again calculate for a different value of chi s just to compare. So, let us take again VDS 0.1 volts, chi s 1.8 phi f, which is volts. Okay. So, with this let us again calculate, all these values. So, here this comes out to be 1.35 into 10 to the power. So, it is quite a large increase in the value of this first term. So, this is one of the factors in the first term. This does not change, this also does not change, because we are again looking for VDS is equal to 0.1 volts. What about this term? This assumes a value, and what about? Okay. So, we can see that there is a large increase here. So, we can see that by when you increase the surface potential by a small value from 1.5 phi f to 1.8 phi f, from 0.705 volt to 8.4 volts. So, for this small increase in is, you can see that the contribution due to the electron charge increases significantly, it increases by several orders of magnitude. So, therefore, you can, so when this assumes a value 1, when the first term assumes a value 1, soon it's only the its exponential nature would make it take over the depletion charge. Okay. So, that is what we wanted to see through some numerical calculations. Now, for this cross sectional view of a MOSFET, this is one section. So, along this line, suppose along this vertical line, either A prime or C prime or an imaginary D prime, along that vertical line, you can say that if you take the cross section along the perpendicular to the plane, you would find it to be this way. So, a small section. So, this is, so the x direction, so you would find that this is the small section. So, you are talking about the surface potential here and the charge inside silicon in this section. So, at each point the local surface potential V would change, and therefore, the charge inside silicon, the area charge looking from the top in that small section would keep on changing. Okay. So, now let us write an expression relating the gate voltage with the surface potential. So, first we observe that in equilibrium condition, we had discussed that the band diagram would look like this. That is because of the work function difference of the gate and the p type silicon in channel MOSFET. So, this work function difference results in an already developed local potential difference in silicon as well as in oxide. So, to make the bands flat, you would have, once you make the bands flat, you would have a band diagram of this kind. So, you have, for this you need to apply a voltage VFB, flat band voltage at the gate. So, what is the, so after this, whatever is the surface potential, so we can now keep on changing the surface potential, and the band diagram would account for whatever is, so once you apply flat band, okay, from here you can take, once you apply flat band voltage, the bands in the silicon region are flat, and now when you apply any other value of gate voltage, there is again band bending in the silicon region and also in the oxide. So, it is as if you have, to the 0 gate voltage case, you have added flat band voltage and then added some other value of gate voltage together. So, it is as if you have added flat band voltage, got this flat band condition, and from here you have applied another voltage, which would result in the band bending that you are discussing. Or for a simple example, you can say that you have applied flat band voltage, got this flat band condition, and again applied a negative of flat band voltage and got this equilibrium condition band bending. So, at 0 volts, this a negative of flat band voltage is as if applied within the metal oxide semiconductor system. So, when you apply any voltage, it is as if this negative of flat band, this flat band voltage is already there. So, already a negative of flat band voltage, band bending corresponding to negative of flat band voltage is already present in the device. So, therefore, when you apply any gate voltage, the band bending has to be seen as if adding to this already existing potential drop from the metal to silicon. So, that is why you add flat band voltage in the expression. So, how would you see? So, you would see that the gate voltage is equal to the drop across the gate oxide plus surface potential with the correction of flat band voltage, because a band bending corresponding to the flat band voltage is already present in the device at 0 gate voltage. So, what is this value of oxide drop across the oxide? So, that is electric field in oxide, that is electric field in the oxide into oxide thickness. So, what is this given by? This would be given by electric field in the charge in silicon divided by electric field in the oxide into oxide thickness. That is because if you see if you look at a Gauss cylinder here, you would find that that is the and at the top lid being in the oxide, suppose the top lid is in the oxide, you would find that the charge in silicon is what is the charge in the Gauss cylinder. That is the reason. Okay, so now this is charge in silicon divided by oxide capacitance per unit area. This is oxide capacitance per unit area. So this, if we so what is this equal to? This is the value of Ez that we had calculated divided by Cox. So Ez is the electric field at the interface. Ez is the value of electric field at the interface. So what is this Ez equal to? This is equal to epsilon silicon. Looking at the value of F, this is we are using the definition of F that we had. So what is the value of Vg? Yeah. And F, the value of F we already know, that is, so as the value of chi s increases, we find so that Vg also increases, but beyond a point, when once this first term starts to dominate, once the first term starts to dominate and become larger than 1, sorry, there is a correction here. When the first term starts to dominate and becomes larger than 1, we would see that exponentially the value of f increases. So what would then happen? So since exponentially the value of f increases, a small increase in chi s would increase this term by a large value, and therefore a small increase in an increase in Vg would almost be a result of the increase in the increase in the value of this term. So a little increase in Vg would almost be compensated by an increase in the value of this term. Chi s would increase by a very small amount. A little increase in chi s would result in a large increase in f, and therefore the increase in Vg would be almost totally be taken care of by this first term. So what are we essentially saying? That the surface potential, once the value of the first term becomes 1, equal to 1, that is chi s becomes equal to 2 phi f plus v. At this point, we would see that a little increase in chi s would then increase the first term, that is electron density, by such a large amount that whatever is the gate voltage, increase in gate voltage would be compensated by would be supported by just a little increase in the surface potential. So surface potential as if does not increase beyond this point. So that is why we find that once the value of the first term has become 1, after that an increase in gate voltage would almost result in a saturated value of surface potential. Suppose you increase the local channel potential, so you are moving from the source edge of the channel to this point where the local channel potential is increasing by a value V from 0, that is. So, in that case, what is the increase in surface potential that you would see? So, the surface potential would keep on increasing almost linearly with gate voltage, but I am sorry. So, let us write down in this region what would be the expression looking like. So, Vg minus Vfb. So, this looks like almost a square law relationship. So, in this region which is encircled, you find that it is almost a square law relation. Whereas, if we look in this region, you would find that Vg minus Vfb is nearly exponential chi s minus 2 phi f minus b by. So, here you find that a little increase in chi s would compensate for an increase in Vgs. Right. So, we can write this in another manner, that Vg. So, this explains. So, here I will end. This explains the fact that chi s does not increase, almost saturates when Vg, the value of gate voltage is such that the first term which is this dominates. Okay. In the function f, the first term dominates, you find that the value of surface potential almost saturates. And in the weak inversion region, where the first term is having a value smaller than 1, you would find that the increase in gate voltage would be almost related by square law with chi s, and you can almost explain, you can almost see as if the entire silicon charge is composed of the depletion charge. So, we will further discuss this in the next lecture. So, in this lecture we have discussed the electric field at the interface, surface potential and the function f, and different terms in the function, how they contribute to silicon charge and also electric field. So, the terms correspond to inversion electron charge, hole charge and the depletion charge. And we discussed how the surface potential would behave in weak inversion and in strong inversion regions with respect to the gate voltage.